Okay, welcome everybody here. So we're at the end of the conference, and we leave all the business and the use cases behind us and talk about fun and hobby projects now. But we also learn a lot from doing these things. So first of all, this is I'm presenting this here today, but it really is a team effort together with Jan van Mulwijk, who is an EME, so an Earth Moonbounce expert at the Wingello telescope, Jan Dijkema from Astron, the Astronomical Institute, who is a volunteer at the telescope, and Frank Zeppenfeld from ESA, who also supported us. So this is the team that actually did the work that I'm going to present here. So what we tried to do is actually to send a LoRa message to the moon with a normal LoRa chip and receive it again with a normal LoRa chip. So Moonbounce is something that is done by radio amateurs almost on a daily basis. So there's nothing special. It is fun to do and it is special to do, but this is not unique in the fact that we send a data message to the moon and get it back. That's done on an almost daily basis. What is special is that we do it with an off-the-shelf chip of a few euros that actually can also receive the answer, because normally it's done with computers and processing and big radios, etc. So we really want to stay as close as possible to a normal LoRa chip. The only thing we have changed is basically the antenna and an amplifier. For the rest, this is all as a normal LoRa device. The reason this works so well is, of course, that the LoRa chips are very sensitive. They are Doppler resistant, so if the frequency has changed a little bit, then that's not a problem. And they provide a lot of interesting data on the received signal. One of the things we had to solve here as well, that we also need to control the telescope from the LoRa chip. So when it switches from transmit to receive, we of course need to make sure that the telescope does the same thing. So that was what we tried to do. As I said, Moonbounce is not, first of all, not new, and it's not very difficult to do. Already in '47, the Americans figured out that you could actually send a signal to the moon and see the echo back. This is the first actual Moonbounce. You see the signal that is sent, and a little bit later, actually around 2.5 seconds later, you see an echo coming back. The real story is probably that in the war, some of these first radar installations already had figured this out, because if you accidentally hit at the moon, you see your own echo back. But the official story is that it was done by the Americans after the war. So this has been done for a long time, and initially they even tried it for communications, because it's also a way to get your signal from one place on the Earth to another signal, but it's not very practical, because you need insane amounts of power and big antennas. So the antenna we had at our disposal is called the Wingello radio telescope, which was the first radio telescope in the Netherlands. And actually, when they built it, this was the biggest telescope in the world. It has been operational until 1997, I think, something like that. And when they built it in the 50s, in 1956, with this telescope, it was the first time they mapped the Milky Way. I mean, for us, it's obvious that we're in a spiral galaxy, but you can't actually see that because of the dust. So the radio is the only way to figure out that we are in a spiral galaxy. And that's what they did with this telescope. So the first maps of our Milky Way galaxy are actually made with this radio telescope. So there's a lot of history here. And even the engineers who built the telescope already used it for Moonbounce and radio contacts as well. After '97, the thing was put out of service, but luckily in early 2000, a foundation was established to restore the telescope, and now it's fully functional again. Actually, with all the modern equipment these days, the thing is better than it ever has been, even if it's for amateur use at the moment. And there's a group of volunteers who actually do astronomy with this, amateur radio, and all kinds of other experiments. And this was one of the things we were allowed to do with it. So the things we had to fix for this setup is, first we need to make sure we can control the telescope, because we have to transmit, so we need to enable the transmitter, which is in the front end of the telescope. But also we need to protect our own equipment, because we're going to transmit with 350 watts, and we need to make really sure that none of that signal comes back into our own equipment by accident, because everything will be broken. So we had to carefully set that up. We also wanted to make a recording with an SDR, such that we can actually analyze the data afterwards. And that gave actually a few results that we had not even thought about when we started this. We do this with a very small bandwidth, so normally LoRa in the LoRaWAN standard is used at 125 kilohertz. Here we use 10 kilohertz, simply because we need the link budget to reach the moon. Another interesting point is that we used actually the LR1110 here. It could have been done with any other LoRa chip, but we simply had this one available. And also, because it's the latest chip, its sensitivity is slightly better than the earlier chip. So this was a good choice to use. Also, we do this in radio amateur frequencies, so of course we need to adhere to the radio amateur regulations. So we had to also send some Morse code with our call sign to identify ourselves before doing this, to make sure we all do this legally. So that was the setup to, oh, there we go. So this is how it looks like inside the telescope. You have all these panels where all the connections are that go up to the dish, and we made a small diagram on how we wanted to connect this. We have two antennas for receive, one horizontal and one vertical, so we simply hooked up both to a LoRa receiver just to see what would happen. Would we see signal on both or on one? And we could just try that. On the bottom, we have the amplifier. So out of the LoRa chip, we get 20 dBm of power or something like that, but to actually drive the end amplifier, we needed 15 watts. So we amplify this to 15 watts, then send it up to the focus point, and there's an amplifier that brings it to 350 watts. So the schematic looks nice and clean, but then when you actually all hook this up on the table, it doesn't look clean at all anymore. But this is basically the same thing that we had in the schematic. Over here, you see two development boards with an LR1110. That's actually the boards we use at Lacuna to talk to the satellite, but in this case, we just removed the antenna. We changed the matching to 430 megahertz from the Semtech reference design, and we use those two as a receiver. Over here, you have the transmitter, which is connected to a small amplifier, and here's the SDR that actually records both what we send to the moon and what we receive. And of course, we had to protect all this with some switches to just make sure that none of that 350 watts would damage our own equipment. Of course, this was just a plan, so yeah, it was a bit of a mystery whether it would work and if it would be easy or not. There were a few challenges actually to signal the telescope to make this work. But ultimately, here we're looking at, anxiously looking if things were going to work. And on the first try that the transmitter actually worked, we immediately got an echo back. That was a surprise to all of us, but it just worked the first time we sent this message. So these boards that I've shown, we were just running our Arduino code on. And on the receiving boards, I had installed a sketch that just printed out every message that was received. Because the signal is so strong, of course, the sending signal we also receive. The boards are next to each other, so they will see each other. And it would also timestamp them. So I just used the Arduino clock to put a timestamp on that. And from that timestamp, we can later calculate the distance to the moon. So, as I said, the first message immediately was a hit. So you see the first board give a green light when it sends, and then 2.5 seconds later, the other two boards give a green light that they received the message. And first we didn't believe that it all worked, but then we actually looked at the results, and it says, well, it received it at an SNR of -4, which means that we had a huge excess of link budget, and I'll come back to that later. So we had way too much power. This was way easier than we actually had thought. It also measures the frequency offset, and this is the difference with the previous one. And it tells you that we actually had a shift of 45 hertz in the signal. The other interesting thing is that actually you see the difference in time. So it was 2.43 seconds later that we received this message. And if you calculate that with a light speed, you see that we traveled 364,000 kilometers back and forth, which actually matches with the distance to the moon. So this must have been a real reception. Because the signal was so strong, so actually in here you see the real received signal as we received it on the SDR. The interesting thing is this was so loud, we could actually hear it, and we have a sound fragment that we can play. Let's see if it works. Oop. Wrong one. Yep. I don't think we're going to hear it. Let me see. If it doesn't work, I'm going to continue, but that's still trying, I think. So if it works, what you will hear is first you hear the signal that we transmit, and then you actually, 2.5 seconds later, hear the echo coming back. And if it doesn't work, we'll just continue. That's OK. Yeah? OK. We go to the next slide. OK, so we also did some publicity about these results, and we got very enthusiastic reactions like, oh, this is just a marketing stunt. And well, maybe it was, but it's fun to do. And actually, we learned a lot from doing this. So I would highly suggest you do marketing stunts like this more often. So here, this is what we actually measured. So it's really easy these days to calculate exactly where the moon is and what the distance is and how much round-trip time you should expect. There are Python modules, and you say, OK, I'm here on the globe, it's this time, how long does it take to the moon? So we can plot that, and then we compare it to what we actually have measured with simple Arduino code. So this is just an LR1110 and some Arduino code. And actually, it matches quite well. It looks like the Arduino code was a little bit, it estimated the distance to the moon a little bit shorter than it really was. I don't know why that happened, but again, we're only talking a few kilometers here on a distance of 300,000, so it's really not that bad. We also did a few other experiments, and Olivier from Semtech also did some calculations on the data we had, and we came roughly to the same number. So I don't know exactly what the offset is, but I'm still extremely happy with how well this worked. So that was the distance, so basically the time it took for the message. We can also look at the frequency error. So because the Earth is rotating, we have a bit of Doppler to the moon. And look at this. I mean, the LR1110 reports the Doppler very exact to what it's calculated to be. So I think this is one of the main takeaways from the project, is that such a simple chip can give you such accurate measurements. You can basically measure the distance to the moon with a simple LoRa transceiver. So let's dive a little bit in the data. We did this 2 occasions. This was the first one where we actually discovered that it all worked. So let's have a look at the SDR results. So now we're looking at the recordings of those bounced messages. Over here, you see the message that we sent, and then we switch to the receive mode, and over here you see it coming back. Well, it's so strong that we can actually even see it in the waterfall. Now we can analyze this because we can measure the delay between this sequence and this sequence. And that's how we also actually get the distance. So if we plot where we think what the delay should be based on the distance to the moon, and we correlate it with the data, we see that the peak we get back from the signal exactly matches with the delay we expect. So after the experiment, we can do all kinds of analysis like this. It's quite interesting how the moon moves compared to us. It looks, of course, we're always looking at the same side of the moon, but there's actually quite a bit of change during the month, and there are 3 motions here that are relevant. I will only look at this one, which is the most important one, and that's simply the rotation of the Earth. We are rotating, and of course, therefore, the moon is passing over us. So at some point, the moon is coming towards us if we stand here, and when the moon is going down, it's moving from us away. But the moon is not a point source. It has a certain size, so not all points on the moon are moving at exactly the same speed towards us. So something on the left side of the moon has a slightly different speed towards the observer than something on the right of the moon. But if something has a different speed, it also has a different Doppler. So if we look into this data, we should actually be able to see different echoes from here than from here on the moon. Of course, none of this is new. I mean, we're just doing it with a LoRa chip, but none of this is new. So in the 60s, they already did this. And I don't know how they have built this, but it must have been a huge job at that time in the 60s to build this with a computer. But they already measured that the first signal you get back has an exact frequency, but then all the later echoes, so the echoes that come from deeper in the moon, from the sides of the moon, that are a little bit further away from us, actually have a slightly different frequency. So we were wondering, would the same effect be able to see in the result from the LoRa message now? And this is the amazing thing. We actually see the same thing. So this is a data message that we send, but basically we use it here as a radar. So it's kind of data sensor fusing, we make a radar image of the moon by sending a LoRa image. Now, LoRa is not even the perfect modulation to do this, and you see also a lot of other reflections here and spoil over. But I mean, the basic shape is already visible. This is the point closest to the moon, where of course the most energy is reflected, but a lot of it comes from deeper in the moon. And this is basically half of the moon depth, and of course the backside we don't see. But just seeing this from a LoRa message was really amazing to us, and it really invited us to look deeper into this, because if this was so easy on the first try, we must be able to do this even better. So we went back in December to do the same thing. And in December, the moon, and just by pure chance, was a little bit further away at that moment. And we actually had the chance to extend the distance record a little bit, because last time it was something like 370,000 kilometers, and now we could go over 400,000 kilometers, which is a nice round number. So we tried that. Unfortunately, it took us just half an hour or an hour too much to get everything working. So by the time the first reflection got back, we looked at the distance, and it was 399 dot something kilometers. So we almost hit the 400,000, but just not. So we did, we did a few of the same measurements, and of course, the whole thing worked just as the previous time. But then we wanted to do some other signals, because if it works with LoRa, we basically can bounce anything off the moon by using the SDR. So first, we start with just a CW. So this is just a single tone, no modulation at all. We just send the frequency, a very strict frequency, and we see what the echo is coming back. And now you see what's happening, because the strongest echo, so the one that is on the front of the moon, is very narrow, because it's a point, so everything has the same Doppler. But the echoes that come back later actually are either positive or negative Doppler. So you see that the signal we sent, which was extremely narrow, actually is wider when it comes back. And that's something we can exploit for making the pictures. So here we do the same thing. And actually here we have a BPSK signal. So this is not LoRa anymore, but something similar. And here we see the echo again. But now you see that we can do measurements which are much more fine-grained than we were doing with the chirps. The chirps are relatively long, and there's a little bit of ambiguity between time and frequency. So there are actually better ways of doing this. The goal was, if we have more resolution, we should also get nicer radar pictures, basically. And that absolutely worked. It even got better. So here you see the same as we did before, and especially this one is nice, because you kind of see the shape of the moon already showing up. And again, this was the same setup, but now we use the SDR. Of course, we still want to do this better. So instead of doing this once, we do this 3 times in a row, but we keep the whole SDR running. So this is all coherent. So later on, we can sum these reflections and even try to get a better image. Now, this is ongoing work. This is definitely not, I think that there's a lot of room for improvement here. But now we're actually to the point where you also slowly start seeing features on the moon. So this is probably a crater. So you get some different reflections, and yeah, you can basically make radar images of the moon. So this was kind of a side effect of the whole thing. When we started, we had never thought that this was possible, but it was kind of what we learned from doing this. So wrapping up, what we actually learned from the LoRa experiment is that, well, we had way too much power. So we had 350 watts, but if we had done this with 10 watts, it would have perfectly worked. So because the dish is so large, just a 10-watt transmitter would have bounced this easily off the moon. So that's a nice result. The other thing is, now we send something back and forth to the moon with a lot of power. But if we see how much power is returned and how much we can decode, that actually means that if you would transmit from the moon with 20 dBm, so the power that comes directly out of the chip, you could actually receive it with this antenna. So a normal LoRa device without any fancy antenna on the moon, we could see here with a dish like this. I mean, there are many of dishes that we could do this with. The other thing is that actually, even with the LoRa message, you have the combination of sensing and data fusion. That has all kinds of options. For example, you can also see where a device is on the moon based on the motions that you see. The next step in this is, so, I mean, of course, on Twitter and all kinds of fora, we have these discussions about the distance. And we first started with balloons. That was with Jan Willem from Zodak, where we had the first balloons getting a distance, and then we got further and further. And of course, this is now like the ultimate one, almost 400,000 kilometers. But first of all, it's just a joke. I mean, what is relevant is how you cover a city, not how you get to the moon. But the signal travels 400,000 kilometers, but in the end, you only moved a few meters on the ground, so it doesn't get you anywhere. So the next step is actually that we're going to try to do this between the US, via the moon, to the Netherlands. With the same setup, not that much power, maybe a smaller dish in the US side. So that's kind of the next step for this. Also, on the SDR, this actually worked so well that there are many more things we want to try there at the Wingello telescope as a bit of a research project. So we're extremely happy on how well this worked. All the data we generated is open data. That's also the policy of the telescope, because as this is run by a foundation, anything you do with the telescope, you need to put online and you need to make the data available to anybody who wants to do the same thing. So we fulfilled that with putting the data there, and we're definitely going to do more of it. And as I said, we're going to do the US to the Netherlands, and who knows, we might get a device on the moon someday and try this as a real LoRa device on the moon. So that was basically it. This was our fun project during the Corona crisis, actually, to have something interesting to do. And oh, I think we're going to try the sound one more time. So the first one was the signal going up. The second one was the signal coming back from the moon. Can we do it one more time? Up, down. Because this is such a small bandwidth, you can actually hear the chirps, which makes it fun to make it an audio fragment. OK, thank you.